So we talked about electric potentials, and now we're going to extend this to talking about equipotential lines. So a line in space that crosses the same electrostatic potential, where the electrostatic potential is constant, is called an equipotential line. Equi meaning equal, potentials, lines of equal potential, basically. In 2 dimensions, or in 3 dimensions, they're called equipotential surfaces. So again, using the analogy I talked about in the last video, as these equipotential lines in an elevation map, equipotential lines are simply lines of constant elevation. Right? So if you're walking up a mountain and there's a path that stays flat and level, it doesn't go up the mountain or go down the mountain, then that is an equipotential path, an equipotential line. If you place a bowling ball stationary on that path, it will not roll because it is an equipotential line. It won't roll along the path. It might roll down the hill towards lower potential, but it won't roll along the path because there's no height difference along the path that would cause it to change gravitational potential energy into kinetic energy. So, equipotential lines are always perpendicular to electric field lines. So another relationship between equipotential lines and electric field lines. Remembering electric field lines in the example here of a simple point charge, the simplest example I can show you. You have a positive charge in the middle. The green lines here extending outward symmetrically from this positive charge are the electric field lines. When we talked about electric field lines, we drew this example in the past. Those are related to the electric field vectors. Equipotential lines are lines of constant potential. If you remember the equation for potential, right? For a point charge, potential was equal to K times Q over R. Well, K is a constant. That's just 8.99 times 10 to the 9th. That doesn't change. Q is the value of the point charge. That doesn't change. The only thing that changes is R, the distance you are from that point charge. Well, this blue circle here has the same radius R in all directions, right? The blue dotted line is a circle of radius small r from that point charge. So since all those points on this blue circle are the same distance r, they have the same potential V. It's an equipotential line. This outer blue line is at a different r, right? So these 2 blue lines don't have the same potential, but all the potentials on this outer blue line are the same because it's the same larger radius all the way around. So it is another equipotential line. So if we use the analogy of, again, topographical maps, if this were a flexible material and I could pull the positive charge towards you, these blue lines would be elevation markers, right? From high to low, as you move away from high potential to low potential. And the green vectors just tell you what direction the object wants to move. In this case, if you pull this up, a positive charge would want to roll downhill, away from this central positive charge. In reality, a point charge in space, right? R is how far you are from a point charge. You can be distance r in 3 dimensions, right? It's a sphere of radius r. So in reality, these equipotential lines are really equipotential surfaces. Imagine this is a sphere of radius r that all has the same potential around this point charge. This outer blue line, again, is a concentric sphere. It has a lower potential, but every point on that sphere has the same potential. The gravity analogy falls apart when we talk about 3 dimensions. So, looking at a capacitor, which we'll talk about, actually introduce in the next video. I've talked about it a few times before this, though. We have a positive plate and a negative plate separated by some distance. The green lines show the electric field between those plates. And since equipotential lines are always perpendicular to electric field lines, I drew in the equipotential lines in blue. So one way to think about it is if this is at plus 5 volts, and this over here is plus 0 volts, which is 0 volts. There is no plus or minus 0. So these equipotential, so this is a potential of 5 volts, this is a potential of 0 volts. So this would be plus 4 volts, plus 3 volts, plus 2 volts, plus 1 volt. Again, a positive charge will go from high potential to low potential. It's almost as if I lifted this positive bar up and showed you, these are elevation markers showing you how the ball will roll downhill, or how the positive charge will move from high potential to low potential. So these are two simple examples of the relationship between equipotential lines and electric field lines. Your book from figures 1909, 1910, and 1911 go into more detail. 1911, I believe they use a capacitor. But 1909, 1910, they start talking about a dipole and the electric field lines and the electric potential around a dipole. So look at those figures, and again, note that the equipotential surfaces, the equipotential lines, are lines where the potential is the same. Now with 2-point sources, you have to calculate the potential twice. What is the potential distance r away from object 1 plus the potential distance r away from object 2? Those r's will be different, right? Because for a dipole, you are closer to one charge than you are to the other. So it's basically summing the potentials from each point charge and then calculating what those potentials are. So look at those figures, look at the figures in your textbook, read through those explanations, and it gives you a helpful understanding of the relationship between electric potentials, equipotentials, and electric field lines.